for Ruben. The upward buoyant force exerted on an object submerged in a liquid, in other words, a fluid, right, is equal to the weight of the liquid displaced by the object. Okay? So what does that mean? Buoyant force has to be equal to gravity, right? Force of gravity. So buoyant force is equal to mg. Well, what is buoyant force? What is mass? Let's do a little bit of, let's see if we can do a little manipulation. We know a formula for mass. Now we're dealing with density, aren't we? So we know this. We know density is equal to, I'm going to do this in red, so we know it's density is equal to what? Mass divided by?
Mass divided by
volume. So mass is going to be density times volume. So we're going to take this and put it in here. And we have a formula then, don't we? So the buoyant force is equal to rho g times the volume. That volume is volume displaced. In other words, this is why an object floats if its density is less than the liquid. Archimedes' principle is what tells us that that's the case. Okay? Now, let's look at an example here. What fraction of a piece of aluminum will be submerged when floating in mercury? Oh, by the way, this right here would be your displaced volume. You see why? If this thing were at a certain level before, once we put this in, this level goes up by this much, doesn't it? And so however much this goes down, however much volume here goes down, it's going to spill out. And this will be that same volume, won't it? All right. What fraction of a piece of aluminum, whose density is 2,700 kilograms per meter cubed, will be submerged when floating in mercury? This also tells you why some parts of an iceberg are below the water and some parts are above, right? Because icebergs are fresh water, but the ocean is salt water. Now, icebergs are really big and really heavy, so most of them are usually below, which is what gets boats. That's what gets boats all the time. They see a little piece and they don't realize there's a huge mountain of ice underneath it, because it's floating, but just barely. I mean, it's barely got anything above most of its. Okay, so it's floating in mercury. So how do we approach this? We know it floats, right? If we know it floats, what do we know? Yep. Let's look at from a sum of forces. What is the total sum of forces going to be? This thing is going to, if it's floating along, it's going to be at what?
Then the buoyant force is going to equal the force of gravity.
Okay, so that's 0. So we know the force buoyant minus the force of gravity is going to be 0. That tells us this. Buoyant force equals gravitational force, right? We'll do the little g. Okay? So what is the buoyant force? What is F sub B? Density of mercury times the gravity times the volume displaced. Okay? And this is for the mercury, isn't it? Okay, so now what is the force of gravity here? Okay, we can't use M because we don't know what the mass is. But what do we know? Aluminum.
Know the density.
Yes, we know the density. So we need to figure out the density for this guy. In terms of density, what is M going to be? Yeah. So it's going to be density of the aluminum times what?
Times volume.
The volume of aluminum times gravity. Now, what you've got to be really careful about is this volume displaced is going to be the amount that is below the water, isn't it? Do you agree? Okay. So, let's see if we can figure all this out. We got a picture here. Or we don't have a picture. We should make a picture. So we got it sitting in mercury. So some of this block of aluminum is above, and some of it is below. Okay. So let's see what we can do here. What are we going to need to know? For pressure terms, what do we need to know? To know what percentage of it, what fraction is it, we're going to need to know how much of it's submerged. So this is H submerged versus the entire height of the aluminum, right? And if we were to draw a free body diagram, FBD, which they always love, what would my free body diagram look like here?
Gravity going down.
Yep, force of gravity going down, buoyant force going up, and they would be exactly the same length, wouldn't they? They're big on physics too for asking you about the magnitude of some of those too. You know those vectors would be the same length. All right, so now we got to figure this out. So let's figure out what's going on. So what do we do now? We set those equal. What do you notice about gravity?
They can cancel out.
Gravity is going to cancel out. Okay. So now we've got rho of mercury. Now volume, displaced. Here's the thing. Volume is what? What is volume? Area times the height. Why would I write it that way? What do you notice about the cross-sectional area? This is going to be the area, isn't it? What do you notice about both of those pieces? Whether it's submerged or not, the cross-sectional area, which is the bottom, is going to be the same for both of them, isn't it?
Right.
So we're going to plug that in. We're going to say the area times the height, what? Submerged? Yeah, if we do so that's going to be that. So we have this is going to be equal to what? Density of the aluminum times what? Cross-sectional area times the height of the aluminum. Now what else goes away now?
Then
Cross-sectional area. So now we actually have it in terms of the things we're given. Well, we don't have it given, but what we know is we want to find that ratio between what? Submerged and unsubmerged. How much of it is submerged versus the entire thing? So to answer this question, what fraction of a piece, we want the height submerged divided by the height aluminum, which means we're going to do rho A divided by rho M, aren't we? I'm just manipulating that equation. Now we can plug in because these are the only two things they gave us, right? So let's plug in. What is the density of aluminum? And what's the density of mercury? Why should we know that it should be in that order and not get it mixed up? If some of it's sticking out, this ratio better be less than what? 1, right? And look at the aluminum versus the mercury. Look at the density of mercury versus the density of aluminum. It's a whole lot bigger, isn't it? So it's a whole lot more dense. So how well is that aluminum going to float? Really well. Which means how much of it's actually going to be submerged? Not much, right? If it floats really well, if the mercury is really, really thick, then the aluminum's mostly going to be on top, isn't it? With just a little bit below the surface. So that number, looking at 2,700 versus 13,600, should be pretty small, shouldn't it? Shouldn't the ratio be fairly small?
Very.
All right. So what's it going to be? I think it's like 0.2.
Yeah.
Okay.
0.2.
So it's not going to be very big. So what did we figure out? In general, this is an important one for you to know. This is sort of a shortcut for you to have. We went through all the math, but what do we know? The fraction of an object that is submerged when it floats equals the ratio of the object's density to that of the liquid. So you can skip all of that math manipulation we just did and just go to a ratio of how thick is what's floating versus how thick is what it's floating in, because that's what it comes down to. So take that and look at this. It says the figure shows a floating block of density 640 kilograms per meter cubed floating in water. Now, you should know the density of water. What is the density of water?
1,000 kilograms.
Yep. 1,000 kilograms per meter cubed. So we automatically know that. So if I want to know how much of that block, H over L, what is the only thing I have to do?
Put the density of water over the density. Oh, no, not the density of the block over water. Fraction of H over L is now.
Oh, be careful. It says what's the fraction of H over L.
Oh.
Did what you just calculated, that 64%, what did we say? The fraction of an object that is?
Submerged.
But if you're doing H over L, what are you really looking for here? How much is?
Fraction of the object that isn't submerged.
Isn't submerged. So we need to do 1 minus
0.64.
Yep. 640 divided by 1,000. So be careful. So this is 1 minus 0.64, which is 0.36. So 36% is above. So be careful with that. I love this. That's the reason why I put this in there, is because you need to know to look and see. When you do that ratio, it's how much is below the surface, not how much is above. So if you're going to do above, you have to find below and then subtract from 1. Right? 100%? All right. So what do we know here? Hold on here. In general,
the density of the object over the density of the liquid equals the amount of the object submerged.
yep. You know what else we know this is called?
What is it called? Specific gravity.
Specific gravity is equal to the density of the material divided by the density of water in particular. Specific gravity only has to do with water, okay? Okay? So if you need to know the specific gravity of something, now, we also know this, don't we? Height submerged. This is a different way to do it, right? Height submerged divided by what? Total height. Okay? How much of it's submerged versus how tall is it all total? So that is an alternative to finding the specific gravity of something. Sometimes that helps. It's easier to do that way, okay? All right. Now, what if the object is what? Submerged. Let's look at a totally submerged object. What do we know? We have an apple hung from a spring scale. When the object is in the air, the spring scale reads 2 newtons. When the apple is fully submerged in water, the scale reads 1.5 newtons. It says calculate the density of the apple. We're going to start with a free body diagram, guys, when we do these types of problems. Free body diagram. So for part A, because we need to know what's acting on the apple. So this is the apple. What forces are acting on the apple?
Gravity.
Gravity is acting downwards. What else?
And water is acting on the
Buoyant force, right?
force.
What else?
You got
It's not hard, the springs for this.
Spring scale, tension, right? Basically, force on the scale. We'll call it force on the scale. You could call it tension if you wanted to, either way. Now, is that apple moving?
nope.
Nope. So what do all the sum of all those forces have to equal if that apple is not moving?
That's to be 0.
0. So let's find out what that expression is. So what are the ones acting upward?
Buoyant force and tension.
Mm-hmm. And then we're going to subtract the force of gravity from it, aren't we? Now we want the density of the apple. So which one of those 3 do we want to isolate on its own side? We're going to need the mass, aren't we?
Oh yeah, I already.
Okay, so which one of those 3 forces needs to go on its own side?
Gravity.
Gravity. So we're going to solve this and say the force of gravity is equal to Fs plus the buoyant force, correct?
Yep.
All right. Do we know F sub S?
F sub S. Oh,
Oh, wait, no, oh yeah, we can, because it says it's 2 initially, and it goes in the water, it's 1.5.
Okay. Well, we know the weight of the apple too, don't we? All right, so let's start plugging some stuff in. Force of gravity. How are we going to write force of gravity?
mg? Or no?
mg, but we don't know m. What are we trying to find?
It'd be density times volume.
Mm-hmm.
Density times volume.
Density.
Density times the volume, right? So we know F sub S here. Buoyant force is going to be what?
It's the density times the gravity times the volume displaced.
Yeah, we're just going to leave the force of gravity alone for a second. What is the, it's going to be what?
Density times gravity.
Density of what?
Of the apple. No.
Not buoyant force. What's buoyant force going to be? Yeah, I'm leaving the force of gravity alone for a second. Let's see if we can figure out what force of gravity is equal to. And then we can set stuff going. That might be easier.
So it's the density of the water.
Density of the water
The gravity.
times gravity times what?
The volume displaced, which
We don't know.
is all, so the volume of the
Yeah.
force of gravity is the same as the volume of air. It's all
So,
displaced.
yeah, so we would know this would be the volume of the apple. But the volume of the apple is equal to what? We know density equals mass divided by
Could be density.
volume.
Could be, or it'd be mass over density.
Yeah, mass of the apple divided by the density of the apple. Okay, so we can actually take that and say F sub S is equal to the density of, or plus, excuse me, the water times gravity, and then we can plug this in. Mass of the apple divided by density of the apple. Okay. Now,
Oh, and then for gravity, since we're doing maybe that's weird.
Because if you multiply on the other side, if we're gonna make volume that, it'll be on, because for gravity, it'd be the
Density of the apple times mass over the density of the apple. That's, does that like cancel it out or?
maybe. But that's okay. We still got the density of the apple on the other side, don't we? So force of gravity is what? Mass of the apple
Yes.
times gravity. Okay. Mass of the apple is, we don't know the volume of the apple, but we do know what this is. We do know what the force of gravity is, though, don't we?
Oh. Oh, okay. So
Okay, so
that would be
it's-
the force of gravity is 2 newtons when it's not when it's in the air, which is equal to the mass of the apple times the force of gravity, or the acceleration of gravity, which is
The force of gravity on the apple at the time. Yeah. The force of gravity is acting on what?
So the mass of the apple would be 0.2 kilograms.
that's,
We're looking for the density of the apple.
Yeah, but that does help.
So let's solve. So we have what?
How are we supposed to do the density of
We also need the force of the spring scale, right?
Well, we know what the force on the spring scale is.
We know the density, or we know the
Yeah.
stuff on the left is 2,
This is 1.5, this is 2,
and then the density of water, we also know that.
which is 1,000. Gravity is 10.
Gravity's also 10.
Mass of the apple. What is the mass of the apple?
It's 0.2.
Should be 0.2 times 10. This one's
0.2.
Oh, I wouldn't even do that. It'd be 0.2. Yeah, you could do 0.2. Because we know, I would just look at it this way. What do we know that's got to be? 2 newtons, don't we?
Yep.
So it doesn't matter either way you work it. All right, divided by what? What we're looking for, right? That's the apple. So now can we solve this?
Yes.
We're going to subtract, right? Subtract 1.5 from both sides. So we have 0.5 times the density of the apple equals all of that, 20 times 1,000, which would be what? No, it's 2 times 1,000, excuse me, not 20. 2 times 1,000, so 2,000. So the density of the apple is what? I'm going to put it over here. 4,000 what? What's the units for density?
Pascals.
Nope, that's
No, not
pressure.
pascals, my bad. It's,
Density is kilogram per
meters cubed.
meter cubed. So do you see why you have to have physics 1 to take this class and be successful? You're diving right into Newton's laws, sort of, aren't you?
Yes.
It's all about, when you talk about fluids and buoyancy, it's all about the force diagrams. That force diagram gave you the equation again, didn't it? Okay, so it says B. Says the spring scale is removed while the apple is fully submerged. Will the apple float up or sink?
Well, the apple's
Awesome.
Just got a single ball.
All right. So part B says it will sink because
PA is, the PA is greater than.
yep, density of the apple is greater than the density of the water. Okay? All right, example D. Is this all kind of making sense so far?
Yes.
We are almost done with this section. A spherical air balloon, yep.
No.
A spherical air balloon has a radius of 9.5 meters and is filled with helium. What is the maximum mass the ball can lift? It gives you the density of helium, it gives you the density of air. Air does have a density. So, let's look at this from a free body diagram. So let's start with the free body diagram. You're always going to use those when you're doing these types of problems. Here's my balloon. We also know it's a sphere. That's going to be important, isn't it? Yes, it is, because we need to know the volume, don't we?
Okay.
So for a sphere over here, we should be thinking the volume of a sphere is equal to 4/3 what? Pi r cubed. Okay, so we know that. So we're going to know volume. We know the radius. So we're going to be able to find the volume of the balloon. But let's look at the free body diagram. What's happening if the balloon is what?
Is that the buoyant force?
Maximum the ball can lift.
So we're looking for.
We have a buoyant force going up, right?
Well, it's gonna be gravity and then also leverage.
Yeah.
And that would be equal. Since we're looking just for how much you can lift.
But gravity's acting on what?
The thing,
The thing that's lifting.
the gravity acting on both of them.
It's gonna-
Both of them. Yes, but what's going to have weight in that balloon? It's filled with
Helium.
helium. So we're going to talk about the force on the helium, right? And the force on the cargo, right? And those, for it to be floating, exactly floating, it's the maximum mass it can lift. It's going to just barely get it off the ground, isn't it? Right? So those will be just barely more than, barely the same, wouldn't they? So the sum of forces, notice I'm starting with the sum of forces, is going to have to be what? 0 for it to float, right? So looking at your free body diagram, what is our statement going to be?
FB minus the other two.
Cargo minus the force of helium, right? Yep. And we could really do force of gravity on the cargo and the force of gravity on the helium if we wanted to be more specific, right? And not forget what we're dealing with here. So, buoyant force.
Oh, yes.
Buoyant force is going to be what?
Oh, yes, the density of the,
Density of air,
Gravity, volume.
and then gravity,
gravity, and the volume of,
The other object, which is the sphere.
but I mean, it'd be the whole object.
yeah,
It's air,
yeah. And the sphere minus or equals, we can put the other stuff on the other side, can we? Equals the force of gravity on the cargo plus the force of gravity on the helium, correct?
Yeah.
So now we got to figure out what we want. We want to know how much the cargo is. What's the mass of the cargo? So this is going to become mass of cargo times gravity, right? We want to know the force of gravity on the helium, but we don't know how much helium is there, do we?
We had to find it because
Density.
we got the density and the volume.
Of the helium times gravity times the volume of the helium. Guess what? We do know the volume of the helium because the helium is contained in what?
And the sphere.
The sphere. Yes. So we know this, we can, instead of calling it the volume of helium, we can just call it the volume of the sphere, because we know it's the same. So density of air, gravity, volume of the sphere. All right. What do we notice about all of these? Gravity.
Just cancel those out.
Cancel out the gravity.
Gravity's irrelevant.
Irrelevant. So the mass of the cargo is going to be equal to the density of air times the volume of the sphere minus the density of helium times the volume of the sphere, isn't it?
Okay.
Well, we can pull the volume of the sphere out, so we only have to do that calculation once. So density of air minus density of helium times 4/3 pi r cubed. So let's figure out what all of those are. Density of air is what?
It is
Minus
1.8.
1.8 times 4/3 times pi times the radius, which would be 9.5 cubed. We can throw all that through a calculator. And we might want to put over here somewhere that we understood that the volume of the helium was equal to the volume of the sphere since it's contained in the sphere, right? Since it's in the balloon, right? What'd you get?
I got 3,986.4.
So 3,986,
Yeah.
and that would be in kilograms. All right. So now the question becomes, do you understand buoyancy? Let's see if you do. I want you to look up there at the exit quiz. I want you to look at your exit quiz on that board right over there. What does the exit quiz ask you?
Which one? Oh, the
Right up there on the board. It says, will an empty balloon
I guess it depends on the pressure of the air, or
Nope.
inside the balloon.
No, it doesn't.
What are we looking at?
Do you see where it says Friday, August 12th? Look under your side, AP Physics 2 Daily Agenda. What does it say for exit quiz? Will an empty balloon have the same apparent weight on a scale as a balloon filled with air?
Yes.
Why?
Balloon expands to suit the pressure that's being exerted on by the air that fills it, right?
Mm-hmm.
So that means that the pressure on the inside of the balloon should be the same as the outside.
Correct.
So you
Except for the fact that if you put a hole in the balloon, what's going to happen? The balloon's going to whee!
Yeah, 'cause it's
Okay, so
The air's actually at a higher pressure inside.
the air's in there, so
'Cause
make
it's-
it way more.
If it
So
were filled with
technically
anything other than the air, you would have either the right or the wrong question. If it's filled with helium, what does the balloon do?
It's lighter.
Floats up, doesn't it? Gets lighter, so it floats. Is a balloon filled with air going to float?
No.
No, it is not going to
In fact,
float.
it's gonna sink.
It might like go up for a second or something like
It's gonna be.
Okay,
What
so
is
it's
that?
just going to sit there
that. But
though.
that's it gliding on the air as its own.
No, if
Yeah,
you like
that's
put it down,
different
it's
because
not
that's
gonna-
that's got to do with
That's like
the
air.
shape rather than air resistance than the other. But it's just going to sit there on the scale, isn't it?
Yeah.
Right.
So we know it's not going to be less. Way less.
It has no reason to be more because the air is the same on the inside.
No.
Thank you. Yes. The air's the same on the inside as it is on the outside. There's no difference in density.
The pressure's higher, but there's no difference in density.
There's no difference in density.
Shouldn't it be that there should? Okay, so if it's gonna go like, that means there's pressure in there, right?
Yeah, but only that pressure is already acting against the skin of the balloon. It's not affecting the mass of the balloon.
But if you took that balloon.
What affects the mass? Density and volume.
But for instance, if you took that balloon into a vacuum where there was no air, it would weigh more in that environment.
Yes,
Because that air adds extra weight.
the air is more dense than what's outside. Yes, the air adds more weight.
In Earth's atmosphere, it's not gonna do that.
That's right.
Like if you went to a planet with a denser atmosphere, would it, and you brought it back here, would it weigh more?
If you put the air from a denser atmosphere in that balloon and you brought it back here, it would sink. Yes, it would. It
So-
would actually burst the balloon. Think
Okay.
about why.
So you're increasing the pressure, but you're not actually increasing the density at all.
Yeah.
Okie doke. That's what I was confused about. All right.
Gravity acting downwards is the same as if you think about it, buoyant force, which is it's sitting down, what's pushing up and pushing down is the same. Gravity and buoyant force are neutral in that case. And it all depends on the density of what's outside and inside, doesn't it? As to whether it floats or not.
So if you brought it from a denser atmosphere, it would pop.
It would weigh more. And it would sink. If it were tough enough skin, it might not, but it would sink, wouldn't it? Okay? If you put it on a scale, it would actually press down, not just sit there neutrally. Okay?
Is the air gonna-
Yeah. It would have to push on
It'd
the
be like
balloon.
a water balloon.
Yes, it would, because water's more dense than air. If you put a water balloon on a scale, or on a counter, it pushes down, doesn't it? So it would weigh more than if you filled it with air. So yeah. But do you see the answer to that question? It's a pretty interesting question, isn't it? It's harder than you think sometimes to think it through. But you got to think about it in terms of what would happen if it were less dense. Okay, it would float, which means if it were more dense, it would squish down. Is it going to squish down? No. So it must be the same. All right.
Okay.
It is 9:43. You've still got about 13 minutes in class. You are welcome